Our next speaker is Lucia Marchetti from the University of Cape Town. She is going to talk about immersive data visualization interactive explorer for volumetric rendering.
Okay, so hi everyone. So my name is Lucia and I work at the University of Cape Town. And I'm also the project scientist within the IDIA Visualisation Lab, and the work that I'm going to present to you today has been developed within that inter-university institute. Today with me, I also have Angus, who is our chief developer for these tools specifically. So if you will have any specific question and technical, he will be able to answer better than me, who I'm merely just an astronomer using the tool and part of the team. So let's get to it. So this is part of a wider research that we are doing at, that we are doing in the IDIA Visualization Lab, which is exploring the capability of virtual reality for data exploration in astronomy, but also in a multidisciplinary, from a multidisciplinary point of view. And why we are using VR? Well, because we want to experiment something that is actually more suited to multidimensional data sets, particles, and volumes that you might want to visualize. It combines discovery and analytics in a novel way, and is also very intuitive, interacting with data that are for native nature in 3D. It displays far more information than standard 2D, and you can implement and explore new methods, which are, in a sense, barely, let's say, their potential has barely been tapped right now in this field of research. And if you want to know more about what we are doing, please visit our website, which is vislab.idia.ac.za. So why we are, well, in terms of astronomical use, the immediate goal that we had in mind when we were exploring VR was actually to visualize velocity cubes that, if you're not familiar, is basically what you see here on the left, where you have basically an image, but that which has a positional definition in the sky, but also have a spectral measurement on the z-axis. And which then gives you basically what is the velocity field that you could see, for example, in this plot here, as we were supposed to do in 2D. But of course, with VR, we can move to do something like this. So instead of visualizing a simple, map of this, we could actually see the warp of the disk of this galaxy immediately as it is. So iDaVIE-v, has a lot of technicalities that I don't have time to go through, but I want to give you just a nutshell on how it is basically thought. So we need it to be cross-platform as much as possible. Virtual reality is natively work on Windows, and that doesn't work well with scientists most cases. But we wanted to try to get to be used at least on Linux system and possibly on Mac at some point, even though the support on there has been discontinued. So it has been developed using Unity plus SteamVR, even though we tested also on Unreal Engine for who knows the alternative to Unity, but actually Unity worked better for the development that we wanted to do. It implements both CPU and GPU operation in hopefully a clever way to optimize efficiency. So the data ingestion and resampling of the data is developed in core memory using C++ libraries. It needs to do resampling most of the cases, because to improve efficiency when you deal with big data sets like data cube in astronomy, you need to be able to visualize very large data sets without having frame problem. So we needed to resampling, and that has been done as well. And the resampling scaling factor can be decided by the user. And the interactivity in VR is actually developed in GPU. And we use the ray matching approach to visualize the volume. We also needed to be used by a non-VR expert, because our community is mostly based by non-VR expert. So we actually built also a GUI that the user can use to interface with the software through, and the interaction is made through menus, hand controllers, and voice commands, which are very effective in VR. because you don't have really a keyboard to play with when you are in VR, and with haptic feedback on your cursor on your controllers, so that you know that a functionality is engaged. The iDaVIE requirements are not that fancy, so actually I'm not gonna read this, but you can check it afterwards. It's really a normal, well, powerful but normal computer that is available for most research scientists. And you can also, of course, the baseline is using a Windows PC, but a Windows, well, Alienware as you may, but also MacBook Pro, the last version that implements a powerful GPU, can actually do the same job. So iDaVIE is a suite and comes in different flavor, but today I'm going to focus on the volume rendering, which is the focus of today's talk. But it can actually, I mean, the underlying software can actually handle also particle, and we are going to use that also in the planetarium to show this. Okay, so this is how it looks like when you start the iDaVIE-v, in this case volume, on your desktop. So you should start a video. So you see it's you have on the left what you would see in VR, and on the right you see the browsing. So you can start up, you fire up your map, you have your header showing up, and then if you have I don't know why it stopped, sorry, oops. Stop the video for some reason. And then if you have an header and if you have a mask, you can also upload that sorry, I'm having problem with the video. Okay, so you see it uploads that, and then when you're done with uploading all the files that you need, it renders immediately what you will see in VR on the left, and you have some basic statistics you can play with, and you can start doing some basics, changing, for example, the threshold to highlight the noise or the sources that you're gonna see. In this case, we are looking at a velocity cube of H1. So all the bright spots that you see in the middle are actually sources, and you can also change the color map and the ratio of your scaling. And if you have a source catalog, you can also visualize that, and that will appear, and you can interact in VR as well. This is, of course, thinking that you might have a source catalog already done on your data. If you don't have it, you can just explore your data cube as it is. So when you start up and you open the VR and you wear the VR headsets, this is what you will see. You have in front of you the cube of your data. This is an H1, so a neutral hydrogen map is a velocity cube. So you have the three-dimensional that I mentioned before. So which is X, Y, and Z, which are declination and velocity on the Z-axis, and you see they are highlighted with different colors because in VR you need some sorts of reference to play around in the volume space. So you have menus, they appear like these, so you can invoke them using voice commands, or you can use the cursor and lasering like we're doing here. But it basically shows up statistics, and you can play around with them in VR space. So this is how it looks like when you start digging into the data. As I said, this is a velocity cube. So every dot, a highlighted dot, is actually a source identified in the code, in the source, in the map. And you see that with the cursor, you can move on, you can visualize different properties on the cube, which is highlighted here because I think in the video you don't see actually the screenshot. So you have basic information on the position, on the velocity, and if you have a catalog, it also says which source is in that catalog that you are exploring. You see that the resolution here is not as great, but because we said we are resampling to visualize the entire cube, but as soon as you zoom in to a subsample or cropping the selection, it goes up to a higher resolution, and you can then visualize the data in their full glory and then start, of course, to do some of your science, which is very good because you can then see the high resolution only in the region that you are interested in, and that improves a lot the efficiency when you're playing with big cube. So one thing that you might want to do, and this is very important for H1, is actually edit the mask. So in this case, you see that the mask is highlighted as a mesh voxels, so the 3D pixels. And you see that most of the sources is inside, but you also see that sometimes the software that you apply to find the mask is actually identified as proper sources, something that is actually an artifact in the code. So in VR, you can actually immediately spot them. And we implemented this paint menu that you can play around, and you basically stick your mouse.
5 minutes.
Yeah, okay.
5 minutes.
Yeah. And you can delete voxel in these cases. So you go and delete features that you're not interested in, and that might affect as well your calculation. For example, if you are interested in the velocity map of these. But of course, sometimes you want to do the reverse. So you can actually, if you think that a feature was not identified, you can also add voxel to your mask. And when you are done with it, you can explore it, of course, and be happy with that. And then you can, of course, save your data and have your new mask to do all the calculation that you need. When you exit paint mode, then you can, of course, do other stuff. You can, of course, start visualizing the results. In this case, this is only what it has been highlighted in your mask, actually with the real value of the map. So you can still, check that you are happy without the mesh in your way. And then you can actually visualize as well the mask per se. So if you feel like the source is actually in your way and you don't really see if the mask is properly done, you can do that. But also you can invert everything and look for residuals. So now we have take off all the signal, the real signal, and we can investigate the cube without them. And it's really important if you want to go and search for new sources that you might not have identified in the cube. We can do some stats through the menus that you've seen. And one, of course, is the immediate thing that an astronomer want to do, especially in H1, is to see, for example, moment map. So when you are happy with your mask, you can actually visualize immediately in this plot the moment map. In this case, is the velocity map. So blue and red means forward and in your direction velocity. But of course, you can also do a moment zero. So basically just the image of your galaxy. Everything is tunable in VR. So we can change the threshold, we can change the noise map. So you can highlight the real features of your data. So this is basically what I wanted to show you. This is just to highlight the fact that iDaVIE-v has been designed with the user interaction foremost in mind, and we actually engaged with the community early on to be sure that we were implementing all the basic requirements that an H1 in this case, but every astronomer that works with DataCube would like to have. So all of them has been implemented already, and the alpha testing is completed. So we have a series of voice commands. We have all the stats that can help you through the data interrogation that you want to do. The beta release of this software is scheduled for December 2020, and is going to be available on the community, and there will be a publication going with it, which is already in preparation and is going to appear at least on AstroPH when we release the beta. It's going to be not the source code for now, because we want to still be able to spot bugs with more users using it. It's going to be an executable that you can just download and run it if you, of course, have an headset and VR ready laptop. And that's it for me. Please visit our website or contact us if you want to know more.
Thank you very much, Lucia. That was great stuff. Are there any? I don't see any questions in Q&A. Has anyone raised their hand? Maybe I was going to ask if have you developed any tools for visualizing polarization data in the same way?
That's like a good question. And Angus, you want to answer this?
So we haven't done that yet. We have tried some polarization cubes. They look a bit strange in VR, I gotta say. We looked at a Stokes Q and Stokes U cube, I think it's the kind of thing where you definitely need to adjust some of the rendering tools and techniques to make it really useful. But yeah, if you've got any requests or ideas on specifics, then that would be interesting to hear. We haven't really explored it other than simply taking a full Stokes cube and trying to visualize that, or one Stokes at a time, at least.
Okay. Well, thanks very much for that.